So I want to try to look at some new series and also kind of put in context some of the results we've already seen. Okay, so these two are things we've already seen. What you see at the very top is just a geometric series. Okay, so that's something we know. We see here Gauss's trick, which is a simplified version of an arithmetic series. Okay, and then after that we have some other examples. Okay, so let's take a look at some of these. Okay, these are examples of series that are well, they're monomials, right? So what we have here is the sum of I, the sum of I squared, the sum of I cubed, and so on. I do want to point out one thing. I'm counting from I equals 0 to n. Before I've done I equals 1 to n, it actually doesn't really make that much of a difference. For these particular examples, it makes absolutely no difference because when I is equal to 0, all those are 0. I just did it for uniformity with some of the ones that are coming up. But anyway, the big thing to notice here, which is fairly significant, is that when we add a monomial, which is of degree 1, what we get is a polynomial of degree 2, right? So we have n times n plus 1, that's n squared. When we're adding all the I squared terms, we get n times n plus 1 times 2n plus 1. So n times 2n, again, that's a cubic, okay? When I'm adding I cubed, I get n squared times n plus 1 squared. N plus 1 squared is a quadratic multiplied by n squared. I get a fourth degree polynomial. So that's really, really interesting, right? So if I add up a polynomial of degree k, I end up with a polynomial of degree k plus 1. That's shocking. Actually, it's not really shocking. What's really going on is there's a relationship between adding up a whole bunch of terms in a series and integrating the terms, right? If you take a polynomial and you integrate them, right, then what you end up with, of course, is a polynomial of one more degree, right? The integral of n squared is n cubed. And this integral, when we go from the integral from 1 to n plus 1, is actually pretty much the same as the sum from I equals 0 to n. Let's take a look at that. Okay, so what we have is the arithmetic or whatever sequence, right? Just some sequence of polynomials. We have a1, a2 plus a3. That's the area of those rectangles. And the reason is the area is because I specifically choosing the width to be equal to 1. So it's width times height. And the height is a1, a2, a3, right? And as you can see, what the area under those rectangles does is it approximates, not terribly well, but it approximates the area under that curve, that red curve, and that's that curve would be like a of x, right? Instead of a of 1, a of 2, and so on. So that's what we have. But we got to find the coefficients, right? We know that the sum of, say, a whole bunch of polynomials of degree 2 is going to be a polynomial of degree 3. But exactly what are those coefficients that make up that polynomial? So this is what we have. I have the sum of a quadratic. Well, we know that's going to be a cubic. And this is kind of a generic cubic, right? I don't actually know what the answers for A, B, C, and D are, and that will make all the difference. So what I do is I come up with some specific kind of test cases, okay? So here is the case when n is equal to 0, right? And when n is equal to 0, then the left-hand side adds up to 0, which means that the right-hand side needs to add up to 0. And the right-hand side, when n is 0, is actually just equal to d, okay? This d actually comes from that, okay? So that tells me that d has to be equal to 0. Okay, so then what we do is I try when n is equal to 1, right? I mean, I can actually choose any different n's that I want, but it makes sense to pick the smallest ones that are going to work, right? So when n is equal to 1, this is actually just 1 because it's 0 squared plus 1 squared, okay? And then this, again, comes directly from the right-hand side. Because n is equal to 1, then that polynomial is just a plus b plus c plus d, right? So that needs to be equal to 1. And then when n is equal to 2, I get this. 1 squared plus 2 squared is 5. And when I substitute 2 into this generic polynomial, I get 2 cubed, that's 8 times a. 2 squared, that's 4 times b. Just 2 times c plus d, right? So that ends up being that, okay? I have 4 unknowns, a, b, c, and d, and I've only got 3 equations. So I need one more equation. Let's try n is equal to 3. And when I do that, then I have n cubed, that's 27a, n squared, that's 9b, n, that's 3c, plus d. Okay, and that should be equal to 1 squared plus 2 squared plus 3 squared, which is 14. Okay, so now I have a system of linear equations. I have a system of linear equations, 4 equations, 4 unknowns. You can solve it using just whatever tools you have to solve linear equations. I actually solved this using MATLAB because I like MATLAB. I could have done it the hard way, you know, and just actually, well, d is equal to 0, substitute. Now I got 3 equations, 3 unknowns, and use Gauss-Jordan by hand. But I'm a computer guy, right? So I'm not going to do that. I'm going to use a program, and MATLAB is there. The answers that it came up with are right here. So a is a third, b is a half, c is 1/6, and d is equal to 0. And now if you look at this, right, then you find that the coefficient of n cubed is 1 times 2 divided by 6 is in fact a third, as expected. Okay, and all the other ones also work out. So this is a way to get to be able to actually discover what the answer should be. And then once you know what it should be, it's not that hard to prove that actually is the correct answer using induction, right? And I would take that second step just in case I made a silly mistake. Okay, now let's look at some other series that look quite different. Okay, so the reason that these are very different is because of this. This series go out to infinity. Okay, so the sum from I equals 0 to infinity of x to the I, that actually has an answer, is 1 over 1 minus x. And of I times x to the I minus 1, again, that has an answer, is 1 over 1 minus x squared. Okay, now one thing I should try to tell you is exactly what do we mean by the sum from I equals 0 to infinity of a sub I, right? You know, what should that be equal to? And this is actually defined in calculus. And the way it's defined in calculus is we take the limit as n goes to infinity of the sum from I equals 0 to n of a sub I, right? So this part here, this is kind of a series, okay, in discrete math. Okay, so we find those results using the techniques that we already covered in this class. And then we have this part where we take the limit. That's actually calculus, right? That's the part where we need to use calculus to be able to do it. And so these series that go out to infinity are defined kind of in the intersection, or I guess I should say the union, discrete math and then kind of elementary calculus ideas. Okay, and just so we're all on the same page, these series are actually called, right, partial sums. Okay, in calculus. So in calculus, you'll hear the phrase, we figure out what the partial sums and then take the limit of the partial sums. That's what's going on to define the sums that go up to infinity. Okay, so let's take a look at these two series and see what they come. Well, if I now look at the partial sum, right, which is the sum from n equals 0 to n of x to the I can actually recognize that, right, because that is a geometric series, right? So the elements are a geometric sequence, and the sums are a geometric series. And the reason that I can recognize that is because if I take successive ratios, so x sub I plus 1 divided by x sub I always get the same value, x, right? And when you have a sequence where successive terms differ by constant factor, x, right, then what you have is a geometric sequence. You know, that's the value of quote r, right? Okay, so we know what the answer is to do this. This is just the geometric series result. So it's the first element minus the element that's right after the last element divided by 1 minus r, right? So where this comes from is this is a sub 0, right, minus a sub n plus 1 divided by 1 minus r, right? R is equal to x. A sub n plus 1 is going to be x to the n plus 1. Okay. Let's take the limit. Okay. Actually, hang on a second. Let me go that back. When I take the limit of this, okay, so in the limit x to the n plus 1 is actually going to go to 0, right, if the absolute value of x is less than 1. Okay, so so the limit of this, right, so limit as n goes to infinity of 1 minus x to the n plus 1 over 1 minus x is going to be 1 over 1 minus x, right? And this is exactly what we say is the answer, right? Notice that the 1 minus x does not change as n goes to infinity because that doesn't involve n. It's only the x to the n plus 1 that matters. If x is actually equal to 1, right, then, well, you have the sum of 1 plus 1 plus 1 plus 1 plus 1 an infinite number of times. So if x is actually equal to 1, this thing does not converge. This thing goes to infinity. And if x is greater than 1, well, the same thing happens, right? It actually doesn't converge at all. So, so this only converges when the absolute value of x is less than 1. Okay, that's the calculus part. Okay, now let's look at the next term, which is the sum from I equals 1 to infinity of I times x to the I minus 1, right? And so what we see is that the derivative with respect to x of x to the I is actually equal to I times x to the I minus 1, right? So what I have is a sum of a whole bunch of derivatives, right? So this is actually equal to the sum from I equals 1 to infinity of the derivative with respect to x of x to the I. Okay, and something that we know is that when you take the derivative of a sum, it's actually the same as the sum of the derivatives, right? Okay, I think we've been through this course far enough that I can give you a friendly warning. We know that when we're talking about a finite sum, right? When we're adding two functions, the derivative of the two functions is in fact the sum of the two derivatives. But what if we have an infinite sum? Is it still true? Well, yes, it actually is still true, but that goes beyond calculus, right? And that actually is the kind of thing that you will study if you take, for example, a real analysis course. So yes, it's actually true under the right conditions, etc., etc. But we're just going to assume that it's a fact. And so since this sum is simply equal to that, then I'll pull the derivative out, right? So from here, I get there. That is the same. And this one, I actually know what it is. It's just the derivative of that term. And then the derivative of that term is equal to this. Okay? All right. So anyway, so I did this before taking the limit. So let's take the limit now. Okay? And let's see what happens. In the limit, as x goes to infinity, as n goes to infinity, then this is x to the infinity, right? This will be 0, this term, okay? That's going to go to 0 when x is less than 1, absolute value. This one here will also go to 0 when x, absolute value, is less than 1. So what we're left with in the limit 1 to n of I x to the I minus 1 is going to be equal to 1 over 1 minus x squared, right? The numerator is just 1. The denominator doesn't change because it doesn't depend on n. And this is actually what we had. Okay. Quick spoiler, I guess, or warning. We're actually going to use these results later in the class. So I'm happy to introduce them as curiosities, right? These are some applications of discrete math to calculus. But in fact, we're going to need these results in the near future, so don't forget them. Okay. Here are some other places where we're going to see them, and we can actually see this right now. So here is a sum, right? These are all the powers of some base value x constant, right? And let's see what happens when we add those. So in the case when x equals 1/2, what we have is 1 plus a half plus a fourth plus an eighth plus dot dot dot, right? And using our formula, that's 1 divided by 1 minus a half, that's equal to 2, right? This is actually a favorite series of us in computer science, right? So I guess if I started at 1, you might even recognize it more. A half plus a fourth plus an eighth plus a 16th plus dot 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 is equal to 1, okay? You can see that this will work if I choose other values of x, like a third or 2/3 or something like that. But this is the one that's most useful to us. Okay. Now, here are some other things that we have, okay? We've been working with sums, right? So this is a series, okay? Now, I don't know if there's a special term for this, but this is a product, okay? So instead of adding a whole bunch of terms, we're going to multiply those terms, right? And the notation for that is to use a capital pi, Greek letter P for product, okay? Likewise, sigma, Greek letter S for sum, okay? And we can use everything we already learned to products. And yeah, that's just the induction tools. All of that stuff will work, okay? Now, sometimes we can do a little bit better because we can actually take a product and take the logs of all the terms. And if you do that, then what you end up with is a sum, right? Because the log of product is actually the sum of logs. And so I take the logs. If I can use all the results that I know about to be able to compute this, right? Maybe I can compute that. Right? So if we can compute that sum, then what we'll do is take e to that sum, and e to the log is just the identity function, so I actually get back the product, right? So if you see someplace that you have to calculate a bunch of products, just remember that trick, right? Take the logs of individual terms, figure out what the sum is, and then raise e to that, and that will give you the answer.